Oh, and model at finite density. Correct.
Thank you, Francesco. Thank you, the organizers, for inviting me. It's a pleasure. So this is not going to be just precisely on the conformal bootstrap. I'm going to discuss about just a quantum field theory. We still be in 2 dimensions. And anomalies will play an important role. So this is a work based on 2 papers in collaboration with Riccardo Ciccone and Lorenzo Di Pietro, which you find it here. So I will start with some motivation and introduction on what was the status in this business, and then I will move on. So this is the plan of my talk: motivation and introduction. Then we will study these models at finite n, first at 0 temperature, and then we will look at thermal effects. We will switch on a temperature. So this is we will study a model of finite density. Okay, so this is the key point here. So what is the motivation? Well, the motivation should be obvious to you. The finite density quantum field theory is of crucial importance in physics, and from a high energy point of view, probably the most interesting still unknown phase diagram is the one of QCD. Here I reported very briefly what more or less we know, what we expect. So just to give you a rough idea, so if this is the typically baryon number fugacity, so we are a finite density, means a finite baryon number. We have, of course, at small temperature and small density, we have the usual hadron matter, our world. Then at high temperature, we have a quark gluon plasma. Then it is expected, so we already here enter here. So this is very well established, of course. Then at very, very high density, which are parametrically higher than actually the most dense object in the universe, so much higher than that, we expect some sort of color superconductivity. So just superconductivity, but for a non-abelian group. Okay, this goes under the name of color flavor locking. I mean, I'm not going to discuss it. Essentially, the difference with respect to the usual hadron matter is that instead of having a condensate for QQ bar, you get a condensate for QQ, which is like the analog of the Cooper pair for usual abelian superconductivity. But then here, this is the most difficult region from the point of view of, this is strongly coupled. So when mu is parametrically large, you are a weak coupling, so you can rely more or less on perturbation theory. But for actual, this mu has to be very large, because for instance, astrophysical objects live in a region of density which is strongly coupled. You cannot really rely on these parametrically large mu results, and we simply do not know really what is the phase of matter there. And as of course you know very well, the lattice is not a great help at finite density because of the sign problem. And then we are, and there are no analytical methods, so we are on our own. You mean this line? No. This line is just a cartoon, so we really don't know whether it is a crossover, first order, second order, any idea. What we know is that for actual QCD, at zero density, there is a crossover with the quark, with the deconfinement transition. No. This is. Let's say that, yeah, again, this is a cartoon. So this is not a cartoon. This is more or less a cartoon. We expect something like that, but here there might be many phases. There might be many phases here. Yeah, we have no idea. Even here, I will say, I mean, in principle, we at a very high density and a very high potential, there might be something here. I mean, it's really unknown. But this is just motivational. I'm not going to talk about QCD finite density, unfortunately. So, but the point about in addition to the general motivation, the reasons why I started showing you QCD is because of several years ago, Deragin, Grigoriev, and Rugopov wrote a very interesting paper where they, by taking the Toft limit, so at large number of colors, they somehow reliably, well, with no rigorous method, but somehow convincingly provided the existence of another phase in QCD, theoretical phase, in which you have, if you denote the usual chiral condensate, let's call it lambda, okay, and now you give it an x dependence, okay, which of course will break translations, but you don't care. We are at finite temperature. Lorentz invariance is already broken. Then they pointed out that actually there is a configuration which dominates, in which the condensate is actually depends on X in the following very simple form. It's what they call the chiral spiral. Q is an arbitrary direction in actual space, and that's what you get, where the modulus of this vector is proportional to mu, the chemical, the baryon density. So they pointed out that since at large n, the Cooper pair, the analog of the Cooper pair goes like e to the minus n, because it goes like 1 over g squared, not a Taft coupling, while the chiral condensate goes like order 1, e to the minus n to the 0. Then at parametrically large n, this spiral will dominate over the superconductivity region. Well, in some subsequent paper by Son and Schuster, actually they found out that in actual QCD, the number of colors, it's not enough to make this phase dominate. So certainly this is not going to happen in actual QCD at this range, but this is still an open question. So there are then other configurations which are rather bizarre, in which the vacuum breaks translations. Okay, but by the way, in condensed matter they are more common as well. So they are there. They are also called the chiral spiral, or also charge density waves, or other kinds of configurations. So given that the status here is complicated, because we don't have access to any analytical method, so it's a good idea to look at a simpler model and to look at the classic simple toy models for QCD. And the classic simple toy model of QCD, one classic toy model of QCD, are the Gross-Neve model. So, no, I'm not going to explain because this will take me. Well, first, I don't really know the detail. It's not a very systematic computation. It's based on some ladder resummation, truncated version. So, no, I'm not going to discuss. No, in actual QCD, we don't know. We don't know, because in fact, later on, Stone has shown convincingly that the CFL, the color flavor locking superconducting phase, actually dominates. So at the moment, the state of the art is that in actual QCD, that chiral spiral at parametrically large density, where you can actually do a computation, is not going to dominate. What we do not know at the moment is what happens at this intermediate density, because we don't know simply.
I guess I'm asking like a kind of a lower level question. Like, is there some effective Lagrangian of which this condensate is a minimum? And so
I'm not aware of any reliable effective Lagrangian for this system. Yeah.
Okay.
So, however, we can address the very same question for two-dimensional models. And again, the typical, the nice two-dimensional model, which is a toy model for QCD, are the Gross-Neve models. So let me briefly review these classic things that I guess you know very well. So what are Gross-Neve models in 2 dimensions? So these are a bunch of two-dimensional Dirac fermions interacting through a quartic interaction. So there are different kind of Gross-Neve models. So I will focus mostly on one, but I want to remind you which is probably the most famous one. The most famous one is this one, which I will call it simply the Gross-Neve model. Okay, so this is the one with maximal symmetry, global symmetry. So the global symmetry here is O to N. So these are n Dirac fermions, but of course the symmetry in terms of Majorana it's O to N. This is the maximal symmetry that you have. So this model is gapped like QCD. It's UV free. And it also has a chiral symmetry break in which some Z2 symmetry is broken to nothing because of the condensate. Psi bar psi gets a vacuum expectation value. Okay? So this is this is one model, and the one which is, however, this is complicated, even in 2 dimensions, so I'm not going to talk about this model. I'm going to talk about another model, which is the Carrel-Grosvenor model, which is this one. So you had not only this interaction, but you had another interaction through the Carrel matrix in 3 dimensions, and in such a way that the global symmetry here, it's a UN vector times U1 axial. So this is the reduced global symmetries of this model. So this model is also UV-free. Sorry, there is a, yeah, thank you. It's going to be hard to, okay, I manage. Yes, thanks. So this is also UV-free, but now in this model, unfortunately, this is it's a gapless model, okay? So it's not gapped. So it's a sort of, yeah, if you wish, a QCD with massless pions. So we will focus on this. We will focus on this Carrel-Grosvenor model. And we will try to understand its phase diagram from first principle, okay? Now, actually, this there has been already some work. I mean, this is a 50 years old model, so you can imagine there's been a lot of work. So let me just remind you what has been done so far. So most of the results in these models have been obtained using large N, because despite the model are easy, but are not so easy that you can get everything at finite N. So most of the results are given at large N. So at large N, well, some time ago, people assuming translations find out a phase diagram that I'm not going to repeat it for you because it turned out to be not the correct one. And you will find essentially the restoration at some high temperature. You will find some phase diagram. This has been worked out actually long ago. But then in a series of papers between 2000 and 2009, Michael T.S. and collaborators using semi-classical arguments pointed out that the dominant configuration at finite density in this model is in fact this Carrel spiral that Rubakov and collaborators proposed conjectured for QCD. So in particular, let me just show you the phase diagram. So this is now for the Carrel-Grosvenor model. Okay, so the phase diagram is way, way simpler than QCD, of course. So we have temperature here, chemical potential, and you just have a line. At some critical temperature, it goes the same straight line, all the way up to an arbitrary mu. And essentially, you have here the symmetric phase, the disordered phase, let's say, in which the Carrel condensate vanishes. And here, you have a chiral spiral. So the condensate is not constant, but oscillates with X. Okay? So being the model gapless and being the fluctuation very strong in 2 dimensions, it's enough, as long as you have an infinitesimal finite density, you will develop the spiral, which is a typical situation for a gapless phase. In a gapped phase, you wouldn't find such a sort of... so if you wish, there is a discontinuity here. If you see trill at mu equal to 0, along this line, of course, you get a constant condensate, but otherwise, you immediately induce it as long as mu is different from 0. So this is what has been established essentially 20, 25 years ago, using this sort of argument. So the main aim of my talk of this work is to, so our aim here is to extend this phase diagram to understand what happens at finite N. And again, since the story is going to be different, we first consider 0 temperature and then finite temperature. Okay? So large n and finite 10 are qualitatively very different, in particular in 2 dimensions. So let me remind you something basic about phase transition in 2 dimensions. Okay, so before entering the details of our analysis, let me remind you that the large n chiral Gross-Neveu model, the one we are talking about, has actually a U1 spontaneous symmetry breaking. You have this U1 axial symmetry. It's actually broken to some discrete subgroup ZNA. Okay? But as you might know, actually, I guess all of you know, this is just an artifact of large n. This is an artifact because you know that there is a quite a renowned theorem by many people, Coleman, Mermin, Wagner, Hollenberg, maybe others, that tells that in 2 dimensions there can't be a spontaneous symmetry of a spontaneous breaking of a continuous symmetry. Okay, essentially the fluctuations are so strong, you know, the propagator of a scalar goes logarithmically, and on R, at least on R2, on flat space, this is impossible, let's say. If you go at finite 10, qualitatively the results should change. So what does it mean to discuss a phase diagram of a theory at finite 10? Okay, so this is what I want to just to remind you. So in particular, there are generically, okay, there are no order parameters. So the fact that this is an operator, this is 0. So the fact that a vacuum expectation value you can't have order parameter for a continuous symmetry in 2 dimensions. So this is, let's say, impossible in 2D. So let me quickly remind you what is the effect. How do we see that large n is actually makes a difference? If you look at the correlation function of an operator in higher dimension, if you look at the correlation function of the two-point function of the order parameter operator, as we know very well, at large distances, this will go like a constant, and then due to the Goldstone, there will be some plus dot dot dot, where this is the power-like decay due to Goldstone, and this constant is because you have a disconnected component here, essentially because you have a one-point function, right? So this is the usual constant, and then this decay. So this is for d greater than 2. In 2 dimensions, since this effect can be there, you have, at most, you can have this. Okay? So you can have a power-like behavior. So if you are not gapped, not exponentially suppressed, you can be power-like suppressed, but you don't have the constant. Now, what can happen is that if you have a theory with some parameter n, the scaling dimension can depend on n. And now we have to pay attention to the limit. So I can take the limit n goes to infinity first, and then the limit of large distances. If you do that, this delta 0 of n actually might go to 0. And if this is the case, you see that at large n, you see an effective order parameter because this factor goes to a constant. Okay? It's an issue of limits. In fact, when you take the large n is the first limit you take. And then you see spontaneous, the breaking of a continuous symmetry in 2D, which is an artifact of your limit. Okay? This, as you know, has been elucidated and worked out by Witten long ago. So when I say what are we looking at finite 10, what are finite 10? So by the way, this is called the strict order sometimes. So the fact that you have an order parameter, ordinary order parameter, we call it the strict order, which is an ordered phase with the usual Goldstone Bose and blah, blah, blah. While in 2 dimensions, we call it, in 2 dimensions, this is, as you know, it's called the quasi-long-range order. So there is a notion of order, but it's not as that one because of the lack of the constant, let's say. Okay, so this is, of course, the most important application of this phenomenon is the BKT transition, okay, which is precisely what I'm telling you here. So in our case, detecting the possible existence of this chiral spiral at finite 10 will be by looking at whether here there will be some other factor, some function of mu, which oscillates. So that's what is our aim. Our aim at finite n, since this is not a possibility, we are going to look at the possible modulation of some two-point function of in the theory to see if this spiral configuration exists. Okay? Okay, so this is essentially the end of the introduction. Any question at this stage? Okay, good. So let's start then. So, so we start at finite n and zero temperature. When I say zero temperature in particular, I mean that we are literally on flat space. Okay, so the space is the actual space is non-compact and the zero temperature. So we are on R2. So let me write once the Lagrangian. Now let's also go Euclidean. Now I use while components, plus or minus. So these are while component, one-dimensional component of our two-dimensional spinors. So let me rewrite then this the Lagrangian before in this basis. A is a flavor index, runs from 1 to n. And then we have the interaction. Now I change a little bit the notation, so I call it lambda s over n. I introduce, although we are at finite n, and this is a Toft-like coupling, so I divide by n, so it's the very same g squared as of before. But now, at finite n, actually you realize that this is not the most general un times u1 axial Lagrangian that you can write. You can write another term, which typically is not written at large n, for good reasons, because at leading order vanishes. But you can at subleading order, with the 1 over n square, you can write it. And in fact, in general, it will be generated if you don't write it. So better to write from the beginning. So there are two parameters, lambda s and lambda b. Okay. So now adding a chemical potential means, from the point of view of I mean, being at finite density, sorry, is as you know, can be mimicked in a Lagrangian description by changing the Lagrangian through some adding the charge, and the charge is simply meaning that in the Lagrangian density we get the current. So this is simply this term here, which, as you may notice, breaks Lorentz invariant, which in particular in 2 dimensions means that it breaks one boost, the only boost you have. Okay, that's it. So the carrier at zero temperature, the analysis is very simple. So I'm going to skip some details because the key tool that will immediately give us the result is non-abelian bosonization. I mean, if you look at the fermionic description, you have to work very hard, but actually it turns out that using this method, things simplifies dramatically. So I remind you that there are different non-abelian bosonization. In fact, at some point I will advocate another one. So the simplest one, known for a long time, is the one in which you take each Dirac fermion one by one, and you replace with the corresponding scalar. Right, so this is a sort of the poor man bosonization. In this case, if you have a symmetry like this one, you will get a manifest global symmetry, which is simply U1 to the n. All the other symmetries of the system will not be manifest in this description. This description is just fine, simply does not make manifest most of the symmetries of your system. For the before adding the interaction, you know, for free fermions, you have other bosonization. In particular, the maximal one is notoriously the West-Domino-Witten, in which you take spin 2n, the covering group of O2n, which is the global symmetry of free theories. You get just the spin 2n level 1 West-Domino-Witten description, which is the bosonization of a bunch of free fermions. In our case, we are going to use an intermediate bosonization, which is the one based on UN level 1 West-Domino-Witten model, which is also a good bosonization. So the reasons why we do not use the maximal one, it should be obvious. We don't use the spin to n because our interaction actually are going to, this deformation here are going to break spin to n to un times u1. So it's better to start with the bosonization with the West-Domino-Witten model, which manifests the symmetry that actually will be there after you deform the theory. Okay? So we will look then at this Lagrangian. We will reformulate using non-abelian bosonization in terms of a UN level 1 West-Domino-Witten model. Okay, so now I just write for you the result. Let me tell you this. So on R2, I mean, there are going to be a lot of subtleties on how you do this bosonization. I will come back to this in maybe 10 minutes or so. But on R2, most of these subtleties are irrelevant. So let's just do the naive bosonization that you might be aware of. Okay. Then we will look at subtleties when you have some holonomies, when you are at finite temperature. So essentially the Lagrangian of the Gross-Neve model can be rewritten in terms of the essentially UN level 1 West-Domino-Witten model that I'm not going to write for you. Actually, let me write it. SUN plus a free scalar. Okay, so this is important. The UN level 1 West-Domino-Witten model, it's an SUN level 1 model plus, if you wish, a U1 level 1, actually level n, a free scalar. So just a free scalar, compact scalar at some given radius, which is an integer value. Okay, so it's a rational theory. And then we have the deformation induced by the quartic interaction, which once you bosonize, this becomes current-current interaction. So these are the SUN current, while this is the U1 current. Okay? Now, while the SUN current actually, well, okay, maybe this is something I have to tell you. So while lambda is a marginally relevant deformation, you immediately see from the form of the J plus and J minus, which is simply, this is simply the kinetic term, that lambda prime is actually exactly marginal, because it amounts to changing the radius of the compact boson, of the U1 compact boson. So you see that something very interesting happens. We have the chiral Gross-Neve model actually secretly has two sectors. One which is strongly coupled, it's actually gapped, gives rise to some spectrum, complicated spectrum, which is the SUN level 1 West-Domino-Witten model, deformed with some current-current interaction. Okay, so this is complicated. It's this part, this SUN and this non-abelian current. And then, which in this limit of R squared, there is a direct sum with another sector which is responsible for the gaplessness of the model, which is simply a compact scalar, okay, with some radius depending on this J plus and J minus deformation. So, by the way, just for completeness, this lambda is equal to 2 lambda s of the original chiral Gross-Neve model, and this lambda prime is lambda v plus lambda s. Remember, lambda s was the original coupling, while lambda v is this additional coupling that at large n typically you don't have. Okay, So now, what is the great feature of having what is the interesting part of having the bosonized version of the model? Well, it comes once you look at the Lagrangian for the fugacity, this L mu, that once you bosonize, this becomes magically depends only on the free scalar. And you get a weird term, which is, of course, is not Lorentz invariant, which is d plus d minus phi. But since this sector was supposed to be free, then you immediately see, due to this shift, that actually the classical level, at any level, okay, so you develop a carrier spiral, because now you see that due to this term, the vacuum expectation value in the x direction of the field is actually zero, non-zero. D plus d minus is dx, and that's what you get. So you immediately see the chiral spiral for any n. So it was not a large n artifact, but actually it's there for any n. Now,
Marco, sorry, a question. Didn't you have a 1 over n square somewhere?
1 over n square? No, but not, once you bosonize, this is
okay.
1 over n, yes. Okay, mu prime is proportional. I don't need to write the formula. This mu prime is proportional to mu with some other factor which depends on the other coupling. It's not important, okay? So this is it's essentially mu. Now, you may ask, can we see directly some correlator? And actually, the answer is yes. We can look at the usual bosonization for this fermion bilinear, which I remind you, it's very simple. So psi A, psi B, this is a matrix. And this is UAB, where U, I haven't defined it here. U, it's an SUN matrix. It's the matrix of the West-Zumino-Witten SUN model, okay? And so it carries the SUN part, and then you have e to the I phi, which is the free scalar. So this is, and then you see that you can look at the psi dagger psi correlator, two-point function, psi dagger psi, at 0, at large distances. And then what you get here, you get trace of u modulo square. This is now the condensate, so these indices are closed here. So you get the trace of u modulo square. Because at large distances, this theory is gapped, so you get only the value of the vacuum. You can forget all the massive states, and then you get this modulation here to mu prime x, which is this carrier spiral we were talking about. And then we have the power-like behavior of the vertex operators here, which is x to the 2 over n minus 2 over n. And then some other correction, which may be, okay, let me write once. Okay. By the way, notice the fact that I was telling you before. If you take the limit n goes to infinity first, this becomes 1. Okay? But this is a finite n. So this is, you see that from a two-point function, you can detect this modulation here. So it's important to talk about two-point function because such kind of analysis has been done also by lattice people that they already had evidence for this chiral spiral configuration on lattice studies. So it's important to give some more quantitative results on where we should, which correlator we should look at to detect these configurations. Okay, so before turning to finite temperature, let's just discuss about this trace U square. Because if this trace U square, yes?
I'm a bit confused. So the action is manifested translational invariant.
The action is?
Manifested translational invariant.
That's right.
And Yeah, and you get a correlation function which is not translational invariant.
Yeah, translation is broken, is spontaneously broken.
So this
So
is
the U1 axial times translation is spontaneously broken to a hypergroup, because if you make a U1 axial translation together with, if you do a U1 axial phase transformation together with the translation, the combination of the two is preserved. But the translation on its own is broken spontaneously. Yeah. And in this, by the way, in this background, you can look then, this is the new, if you wish, this is the background you have, you can look at the excitations, and you do have massless excitations, which are essentially some sort of phonon excitation, which is precisely this, the excitation of the compact scalar themselves. So it's very easy to find out. Yes. So yes, there was a little point. I was assuming that trace of u is different from 0, because if trace of u vanishes, the Stupin function at large distances simply vanishes. So that coefficient there, it's not the dominant one. So let me give you three good reasons to think that this trace of u has to be non-zero. So I will be brief for lack of time. So the first one, oh, by the way, trace of u different from 0, its signal, it's an order parameter for the ZNA symmetry breaking. Because u, remember, u transforms as G left, U, G right. G left and G right are the global, the two copies of the global symmetry of SUN times U1. And you see that, sorry, G dagger. So you see that if I take an axial transformation, U transforms. If I take a discrete transformation in the center of SUN axial, the U transforms again. So if trace of U is different from 0, it's a way of detecting the spontaneous symmetry breaking of the axial symmetry ZNA. And actually now I list you 3 reasons to believe that this trace of U in fact is different from 0. One is the fact that SUN West-Duino-Witten model at level K have a mixed Toft anomaly which involve PSUN vector times this ZNA axial. So I don't have time to show you where this anomaly come from. Sorry, I forgot to. K sorry, the SUN mixed anomaly unless K is 0 mod n. Sorry, for 0 mod n, the anomaly cancel, and generically you have this anomaly here. It's a Toft anomaly, okay, which is a mixed Toft anomaly between two groups. PSUN, you can see it's not a mystery. PSUN, because you see that if I make a transformation of a vector transformation for the center of SUNV, you see that U is invariant. So PSUN is actually the faithful symmetry of U. Okay, and so this is telling us that the vacuum cannot be trivially gapped. Now we are not talking about the Carl-Grossenevin model. Pay attention. We are talking on this SUN level K deformed with some JJ interaction in isolation without the compact scalar. Okay. So this is an indication that perhaps trace of U is different from 0. As you know, anomaly arguments do not allow you to tell you precisely what's going on. They can only exclude things. So here we are excluding the fact that the vacuum is trivially gapped. There is only one vacuum. Something more complicated has to happen, but we really do not know precisely what. Another argument, by the way, the natural argument which which typically is the one that occurs, is if you have a spontaneous breaking of a discrete symmetry, automatically you get many vacua. In this case, if Zn is spontaneously broken to 0, you get n vacua immediately, right? So, but there might be other situations, other possibilities, but there are 2 other reasons to believe that this is the case. Semi-classically, if you do an abelian bosonization, this naive bosonization I was telling you about, the JJ deformation becomes some sort of sine Gordon-like potential, okay, just a generalization of the Sine-Gordon potential, and semi-classically you find out that there are in fact n vacua. So this potential has n vacua. Of course, in perturbation theory, so this is also not enough. So it's only semi-classically you find n vacua. But then the third evidence is that if you take the n equal to 2 case, n equal to 2 case is particularly simple because the SU2 level 1 West-Zumino-Witten model is actually itself a U1 because SU2 level 1 is equal to U1 level 2. And then you have two scalars. And the JJ deformation is simply a cosine. And then we are going SU2 West-Zumino-Witten model is nothing else than the Sine-Gordon model. In the Sine-Gordon model, thanks to integrability, Zamolodchikov et al. Long ago find out formula that allow us to compute. Actually, trace of U can be computed using integrability, okay, for n equal to 2. And this computation reveals, so you get a complicated function, of course, which actually interpolates with the semi-classical regime, and it actually gives you 2, in the sense that it is consistent with having 2 vacua, which are naively the 2 vacua that you have when you have a cos phi potential, one at 0, one at pi, okay? So from now on, I assume that this is enough evidence to say that trace of U is different from 0, and we have n vacua. So in the SUN sector. Okay, so this is enough for the analysis, the simple analysis at 0 temperature. Now let's look at finite temperature. Let me see how much do we have? 15 minutes? Okay. So at finite temperature, I mean, just to make it the story simple, it means that we are just on the cylinder, okay? So we take a thermal circle, and then the space direction are just non-compact, okay? So this is the simplest configuration you can make, but still there is an issue, because there are 2 spin structures along the thermal circle, right? So there are 2 spin structures. Well, if you want in actual temperature, an actual real physical system, fermions should be antiperiodic along the thermal circle, but theoretically we may want to look at what happens if fermions are periodic around the thermal circle. So this is another possibility that you can have. It's not very physical, but you can conceive it. And in fact, the physics will drastically depend on which periodicity condition along the thermal circle for fermions we take, okay? Now, I think I had to maybe wrap up a little bit. So non-abelian bosonization has to be completely reconsidered whenever you have non-trivial holonomies, because many things that I put under the carpet now reveals themselves. So for instance, how can a fermionic theory be dual to a bosonic theory? The bosonic theory, whenever you put on any manifold, does not depend on the spin structure, because you have bosons. They don't care about spin structure. But if I have a fermion theory, Carrel-Gross-Navet, just as I was told you, they do really depends on how you choose along your cycles the periodicity of your fermions. So the 2 things cannot be the same, as I told you before. So the Carrel-Gross-Navet model cannot be dual to the West-Zumino-Witten model when you go into the details. So the actual full equivalence on any Riemann surface is more complicated, and I will sketch you, hopefully without complication, what is the full story, okay? So the full story, we can look at the case in which we switch off the deformation, just free fermions, okay? So just for the simplicity, let's look at the maximally symmetric case. So let me denote by B the spin 2n level 1 West-Zumino-Witten model. So this is not the one I've been using, but this is only for the sake of explaining what happens when we have non-trivial spaces. And let's call it F, simply n the free Dirac fermions. So these are the 2 theories that are supposedly dual to each other. So one is the bosonization of the other. Okay. So just I write for you the result. let me write in this a little bit of a fancy way. I hope I will explain it to you. I don't need much of all this technology here, but the bare minimum to maybe yes. Okay. So this is the bosonic theory. This is the fermionic theory. Then what we had to do, we had to attach what is called a topological, the simplest topological quantum field theory, which has an amazingly simple partition function. This partition function is the following: is 1 if you have so-called even spin structures, and it's -1 if you have odd spin structures. Now, odd or even spin structure mean how many fermions you have mod 2. Okay, if you have just if you look at the index theorem, whether you have even or an odd number of fermions. So if you have an even number of fermions, this is called qualify as an even spin structure. If you have an odd number of fermions, it's an odd spin structure. Okay, and this theory here, it's a very simple topological theory, which essentially is a bunch of signs, 1 or -1, depending on the spin structures. So this object is what is, if you wish, the new entry with respect to what we were doing before, and this takes care of the fact that the fermionic theory has spin structure, does not depend on the spin structure, and all this spin structure info is within this ARF. But this is not the end of the story, because then you have to do a modding, you have to gauge something, which is a Z2 symmetry here. Left mean that this is, you can choose either the left or the right, the global symmetry of the spin to n. It doesn't matter. You have to use a Z2, you have to choose a Z2. I don't want to enter into more details into this. There is you can write the formula for the partition function. This formula, by the way, works in any manifold. So this is the real story, okay? So you can write the partition function for the fermionic theory, and then in order to rewrite in terms of the bosonic theory, you have to do this manipulation. You can do the other way around. Given a bosonic theory, if you do what is called naively summing over the spin structures, you get, so if you have a fermionic theory, you sum over the spin structure, you get a bosonic theory. So this is from the string theorist aficionados. This was something that has been done for many years, the sum over spin structures to get the various string theories. Okay, but I'm not going to enter into much of the details. I will try to avoid all these technicalities here. This is just to warn you that the story now is a little bit more complicated. Okay. Okay, and so finally, another important thing is that if you are finite, let me say something now again general, so finite n and finite t, there is yet another common law. So we were saying that in 2 dimensions, finite n Coleman theorem forbids the breaking of continuous symmetries. And if you got finite t, essentially finite t, if you integrate out the Matsubara modes, you are essentially in a quantum mechanical model. So we land in quantum mechanics. And the law is that if you are at finite temperature in 2 dimensions, any symmetry, even discrete, is immediately restored. So the fluctuations are so strong that the critical temperature of any transition is 0. Okay, everything is restored. And the best way to see is that in quantum mechanics, instantons always give rise to a unique vacuum. This is the usual, let's say, law. And now we finally arrive at the title of my talk. And actually, this law is known to be not always correct, because sometimes you have a Toft anomaly again that protect you from having a single vacuum. So if you have a quantum mechanical model with an anomaly, with a Toft anomaly, then the vacuum cannot be unique. It's impossible, because it's inconsistent with the fact that there is an anomaly. And in fact, this has been shown in various works. The simplest and most notable case is the one of a free particle on a circle, which you can add a theta angle. And if you consider charge conjugation and shift symmetries for the free for the free scalar. If theta equal to 0, everything is fine, but if theta is equal to pi, you get a Z2 anomaly, which is telling you that this system cannot be trivially gapped. In fact, you compute the spectrum, it's a free theory, it's very easy to compute it, you get two states, but the anomaly is more than that. The anomaly is telling you that you can arbitrarily deform this theory. If you do not break neither charge conjugation nor these shift symmetries, you are ensured that whatever deformation you make, you are going to get a non-trivial vacuum. And indeed, this is the case because of essentially instantons get suppressed. So here is going to be the very same story. We are going to show quickly that depending on the periodicity of the fermion, we will have a Toft anomaly, which for periodic fermions reveals itself and is going to tell us that the vacuum, essentially at any temperature, the broken phase remains, persists at any arbitrarily high temperature, while for for antiperiodic fermions, this is not going to be the case. For antiperiodic fermions, essentially this anomaly gets broken, is no longer there, and you get the usual common law story that nothing is seen anymore. Okay, so the correlation function decay with the power, and the Scara spiral in particular is not going to be seen anymore. Okay, so due to time reasoning, I think I will have to show you only a few things. So I was supposed to show you this what is the anomaly responsible for this effect, but I'm not sure I have time to do that. What should I do? Yeah, maybe, okay, let me just see in words. So if somebody interested, I can tell you more, but I don't think I have time. So the simplest case would have been with the compact scalar. Okay, let me just tell you, if you have a compact scalar, you may know that you have a U1 to U1 global symmetries, which are simply the shift of the field plus a constant, and then the shift of the dual field. So these are two parameters running from 0 to 2 pi, so they have two U1s, and this is a symmetry of a free scalar. And if you look at the Z2 here, alpha p equal pi, so this is a Z2 subgroup, alpha w equal to pi, this is another Z2, and also charge conjugation, which is another symmetry. So you have three symmetries here, charge conjugation, P, I call it P, this generators alt alpha equal to pi, and let's call it a W, the Z2 shift here. So these are three Z2 generators, and you can easily show that actually they have a Toft anomaly among themselves. This Toft anomaly is such that, so there is a Z2 Toft anomaly here among these three generators. Actually, there are many other anomalies, in particular a free scalar has a continuous anomaly between the momentum and winding, but that's another story. So this anomaly involves these three factors, and a similar anomaly will affect the full West-Zumino-Witten model I'm telling you about. So this anomaly is such that actually when you fermionize, you get a diaedral group. So out of this symmetries, you get a D8 group. So this is in the fermionic theory. You get this importantly, the deformations of these quartic deformations do not break these Z2 symmetries. Z2 symmetries are very robust, so they are not broken. So this anomaly will persist in the actually strongly coupled theories. Okay, and actually it turns out that in this D8, there are two possible situations. So if the fermion is antiperiodic, so antiperiodic, let me call it a Navier-Schwarz using this string theory language. So a Navier-Schwarz fermion, antiperiodic, D8 is linearly realized. Linearly realized. It's another way of saying that there is no anomaly on the spectrum. Okay. while for Raman fermions, periodic fermions along the circle, T8 is projectively realized. So we have an anomaly, okay? So the anomaly persists. It's actually not uncommon that anomaly persists upon compactification if you have periodic fermions. Look, just think at the Witten index, no? The Witten index, it's a topological quantity, but only because fermions are periodic. In fact, the -1 to the f precisely does this. Makes fermions periodic along the circle instead of antiperiodic. Okay, so can we be more precise, or if you wish, more quantitative in detecting if we really have these differences and whether this Kara spiral is seen or not? Because so far the Kara spiral was not even mentioned. I just told you that independently of the fugacity, we have two different behavior of the model depending on the spin structure of the fermion. Now we can go back at our original system and look at the two cases, fermionic, antiperiodic fermions, periodic fermions. And then we can look at the Tupen function as before. So we compute some Tupen function, we take the large distance limit, and then we look at what is its behavior. Now, unfortunately, the original Tupen function is too hard. So psi dagger psi is too hard, because now, due to the fact that the space is compact, the SUN and the UN are actually related. I mean, the gauge invariant operators are product of the two. I cannot really forget the SUN part as we did on R2. Okay, so this is complicated. This would require me to compute correlation function in the SUN deformed theory, which is a strongly coupled theory, and it's hard. Okay. So, however, we can look at the specific operator, which is the determinant of this matrix, psi dagger A, psi B. Okay, let's call it OF. This is a big operator, and this operator is nice because once you bosonize, it becomes simply an identity in the SUN sector, and then e to the I phi n phi r over r. So the bosonization of this specific operator is simply a vertex operator in the compact scalar. Still hard because you have to have control on the partition function of the SUN model. Okay, but doable now, at least in some specific limit. And the specific limit is this one. So if you call M the mass gap of the SUN sector, okay, in this specific regime we can do the computation. So T for small temperature and large distances. Okay, the Tupen function of this operator OF here behaves in the following way. So it's just an amazingly simple chiral constant term when you have around you see look like strict order because not even its power like suppressed, just a phase depending on mu. This is for Raymond fields, while for Nemeth-Schwarz you have what you would have expected by usual naive argument. So you have an exponentially suppressed correlator weighted with modulated by this factor. So this Kara spiral factor still is there. If you remember, on R2, it's a very simple fact. But now it's totally invisible because you see that X over T is it's very big, and then this factor kills the full correlator at any. I mean, this regime, this is huge, right? So in the Nemeth-Schwarz, you no longer are the correlator. It's so damped that there is no way in which you can look at this spiral configuration again. Now, there is another way to check this computation, which I will just mention. Large N. We can go back to large N again. At large N, we use the usual Abbas-Stratonovich technique that we like and love. So let me just emphasize, if I have a minute. So you introduce a complex Abbas-Stratonovich field delta, and then the free energy that you can compute at large N is simply given by So this is, it will be a completely standard computation, if not for two things. The first is that there is a chemical potential, which is not a big deal. I mean, the chemical potential you can reabsorb in the periodicity of the fermions, changes a bit the Matsumara modes with some other imaginary factor. It's very easy to deal, okay? What is less easy to do is to now assume that the Haber-Satonovic field is actually x-dependent on the vacuum. So typically at large n, you take the Haber-Satonovic field to be a constant, you compute effective potential, and then you are happy to see that you see some non-trivial vacuum expectation value. Here, you get the x-dependence. If you keep the full x-dependence, the computation is not so easy, but you can take, since if you wish, we already know the result, so we take as an ansatz a particularly simple configuration, which is a constant times c to the 2i qx, where q is an arbitrary parameter. So you have two parameters, m and q, and then you minimize the free energy. And what you get is precisely what we expect. So you get that, first of all, so if you minimize f, you get that q is either 0 or mu, and mu m is either 0 or the dynamically generated scale. And what is more important, well, not more important, but at least for us, it depends crucially on the spin structures. So if you have NS fermions, there will be a temperature T above which the symmetric phase is restored, so you get m equal to 0. While for Ramond fermions, you have this persistency of the broken phase. For Ramond fermions, m is different from 0 for any temperature. Okay. So yeah, I think it's I have to wrap up. So I don't have time to tell you about the Grosvenor model. So just summarizing, so we find out, so people have found out that chiral spiral configuration do exist at large n in the chiral Grosvenor model. So they were conjectured to exist in QCD. In QCD, we had no idea whether they exist or not. And in this work, we argued and showed that they actually persist at finite n, with the caveat that depending at finite temperature, the system, because of anomalies, the chiral spirals can be seen for periodic fermions, but for actual true thermal configurations, it's exponentially suppressed and then disappears. Okay, so thank you very much.
So we have time for some questions.
Yes, there.
What is lambda in this last equation? M is being 0 or lambda, this capital lambda?
Yeah, sorry, I was referring to my previous, M here is an arbitrary parameter that you minimize, so it's a free parameter. This lambda is the one, it's the value of the condensates at 0 temperature that you know from the usual large n for constant configurations, yes.
Any other question? Maybe I have a short question. What's the minimal n where in QCD you would see this effect? You said that for n equal 3 is not dominating.
Yeah, I don't remember the precise number, I must confess. So I think Schuster and Sono were pointing out that NC has to be bigger of 1000 NNF, something like that. Which clearly, so these are the numbers. Now, I'm not totally sure about the precise digits here, the figures, but this is the order. Yeah.
Okay, if there are no more questions, let's thank Marco again, and we go to lunch.